Okay, so in this video we want to review function notation. It is essential that you can work effectively with function notation and you can understand it, particularly with your CAS. Being able to work effectively and efficiently with function notation makes for efficient use of your CAS calculator. We'll talk a bit more about that a little later on. But equally, function notation is used frequently in this course, and it's important to be able to use it and use it accurately and to understand it. So in a previous video, we established that a relation is a function if it is one-to-one or many-to-one. And so the key feature of a function is that no matter what the input is, a function will produce a unique piece of output. Okay, so that means that I can pick any x value, and that x value will just give me one y value. Okay, there might be other x values that give me that same one y value, but what it means is any number that I shove into the function spits out just a single number. Okay, it's not going to, unlike a one-to-many function, for example, which looks like this. This particular x value spits out two different y values. However, in a function, no matter what x value I pick, I just get one piece of output. Okay, so if a feature of a function is that for any input value we just get one bit of output, then we actually don't need a different letter to talk about the output. The output is a direct result of applying the function to the input, f of x. Take our input value and apply our function f to that input value. Okay, so if the input to the function is x, the name of the function is f, then we call the output f of x, applying function f to piece of input x. Okay, so for example, if our function f is to multiply the input by 3 and then add 4, if our input is x, f of x is 3 times x plus 4, 3 times the input plus 4. If our input is 2, f of 2 is taking 2, multiplying it by 3 and add 4. So 3 times 2 plus 4, which is 10. If our input is 5a, applying function f to 5a, which means multiply 5a by 3 and then add 4. So 3 times 5a plus 4. f of 5a is 3 times 5a plus 4, which is 15a plus 4. If our input is x squared minus 2x, we multiply x squared minus 2x by 3 and then add 4. f of x squared minus 2x, a result of applying our function f to x squared minus 2x, is 3 times x squared minus 2x plus 4, which simplifies to 3x squared minus 6x plus 4. Whilst we conventionally use the letter f as the name of a function, any letter or symbol could be used. Obviously we avoid some letters for particular reasons. E has another meaning, I has another meaning in maths, so we tend to choose our letters a bit carefully. We'll probably use f first, and then if we've used f we would go to G next, and then we might use H. We wouldn't use I, we then might go to a different letter. Regardless, it doesn't matter what you call it, f is just simply the name of the function. Okay, so if, for example, we have a different function, whose name is g, function g, and g is the sum of the square of the input and 5 times the input, which means that if the input is x, g of x, the result of applying this rule to the input x is to take x and square it and add it together with 5 times x. Okay, the square of the input, which is x squared, and 5 times the input, which is 5x, are added. Similarly, if the input is 2, g of 2 means that we do this rule to 2. So it's the sum of the square of 2 and 5 times 2. Okay, so it is 2 squared plus 5 times 2. 4 plus 20. No, sorry, 4 plus 10, which is 14. If our input is negative 3, you can think about it algebraically. We're just replacing the x value with negative 3. So it becomes negative 3 all squared plus 5 times negative 3. Please be careful how we write negative 3 all squared. Negative 3 all squared is not the same as negative 3 squared. This is equal to positive 9. this is equal to negative 9. Order of operations, powers happen before multiplying, so 3 squared happens before you then multiply it by negative 1. Whereas here, you're multiplying the 3 by negative 1 first, because the brackets override that, and then you're going to square it. Okay, so be clear about that distinction and make sure you write what you mean. If you accidentally, just through laziness, write negative 3 squared when what you actually mean is negative 3 all squared, this isn't right. You're going to lose marks for that. The notation means different things, and one of your jobs this year is to understand that notation and be able to speak fluently in it. Okay, it's a language you have to learn. Negative 3 all squared is positive 9, plus 5 times negative 3 is minus 15, and so this is negative 6. G of x plus 1, we take our new input and we replace x with that. So we're going to have x plus 1 all squared plus 5 times x plus 1, which means we get x squared plus 2x plus 1, that's just expanding out the perfect square, plus 5x plus 5, expanding out the second bracket, and now just collecting like terms, x squared plus 7x plus 6. Alright, let's have a go at another one. Function h is the square root of 10 minus the input. So if the input is x, h of x is the square root of 10 minus x. If the input is 1, h of 1 is the square root of 10 minus 1, which is the square root of 9, which is just positive 3. We didn't take the square root. H of 1 is equal to the square root of 9. Okay, in the same way that if I said, y equals 5, I don't mean y equals positive or negative 5. When I don't write a symbol here, I mean positive 5. When there's no symbol here, it's the positive square root. Okay, it's not either of them. If the question was x squared equals 9, then x equals plus or minus root 9, which is plus or minus 3. If x equals root 9, then x just equals root 9, which is 3. Okay? Alright, if the input is negative 5, h of negative 5 is the square root of 10 minus negative 5, which is the square root of 10 plus 5, which is the square root of 15. That's the third in simplest form. If x equals, if the input is 3a, then h of 3a is substituting 3a into the rule, which says we take the square root of 10 minus the input, so the square root of 10 minus 3a. We can't simplify that any further. If the input is x plus 4, h of x plus 4 is the square root of 10 minus, now careful here because it's minus all of x plus 4. So that's the square root of 10 minus x minus 4, which is the square root of 6 minus x. Okay, let's have a look at a series of examples considering these three functions. F of x is a quadratic function, 3x minus x squared. G of x is a square root function, square root of x minus 2. H of x is a hyperbola, a reciprocal function, which produces a graph that looks like a hyperbola, 1 on x plus 1. Okay, find h of 4. That means replacing the input in h of x with 4. So if h of x is 1 on x plus 1, h of 4 is 1 on 4 plus 1, 1 on 5. F of negative 4 means replacing the input, replacing x in f with negative 4. So that is 3 times negative 4 squared, not negative 4 squared, just 3 times negative 4 minus negative 4 squared. So that's negative 12 minus 16, which is negative 28. G of 0 means make the input in g of x 0. So replace the x's with zeros. Square root of 0 minus 2, square root of negative 2. G of 0 is undefined. Can't take the square root of negative 2. G of 10 on 3, replacing x in g of x with 10 on 3. 10 on 3 minus 2. 2 is 6 thirds. 10 thirds minus 6 thirds is 4 thirds. Square root of 4 thirds. Please be careful how you write your square roots. Okay? Don't be ambiguous about whether the whole fraction's under the square root, whether it's just the numerator. Be clear about what's happening. This is, given that 4 is a square number, I would probably simplify that. It's the same as root 4 over root 3, so that's 2 over root 3. And we can leave it as that, or if you rationalise the denominator, by multiplying both the numerator and denominator by root 3, then you'll get 2 root 3 on the numerator. Root 3 times root 3 on the denominator is just 3. This is perfectly fine in methods. You don't have to give answers with rational denominators. You do have to give fractions in simplest form. You don't leave decimals in fractions, all those sorts of things, but you can give a fraction with an irrational denominator. There's no issue with that. H of 1/4. Okay, so h is 1 on x plus 1, so h of 1/4 is 1 on 1/4 plus 1, which is 1 divided by 1/4 plus 1. 1 is 4/4, so it's 1 divided by 5/4. 1 divided by 5/4 is 1 times 4/5, and so that is 4/5. F of 0.2. F is 3x minus x squared, so that is 3 times 0.2 minus 0.2 squared. 3 times 0.2 is 0.6. 0.2 squared is 0.2 times 0.2. You can just think about it as 2 squared, which is 4, but then you have to think about how many, so if 0.2 squared is 0.2 times 0.2, there are 2 digits after the decimal place in that multiplication, so your answer needs to have 2 digits after the decimal place. Okay, so it has to be 4, but it has to be 4 so that you have 2 digits after the decimal place, so 0.04. 0.6 minus 0.04 is 0.56. Now, if you're no good at decimals, I'm not a big fan of decimals, 0.2 is 1/5. So you could do 3 times 1/5 minus 1/5 squared. And one of the reasons I prefer fractions is when you're squaring fractions, they're just whole numbers. It's just being able to do 1 squared and 5 squared. So this is 3/5 minus 1/25, which is 15/25 minus 1/25, which is 14 on 25, or 0.56, whichever you feel more comfortable with. Alright, G. F of 3x, so f of x is 3x minus x squared. F of 3x will be 3 times 3x minus 3x squared. Okay, so all we're doing is wherever there is an x in the function, it gets replaced with 3x. Okay, the input x becomes 3x. So this is 9x minus 9x squared. There's nothing more we can do to simplify that. You can factorize it, but can I be really clear about the fact that factorised or not factorised, these are just as simple as each other. They are both in simplest form. So if you haven't been told to express your answer in a factorised form, or express your answer expanded out or in a particular form, either of those are perfectly fine. There's no need to go to this level here. It's not more simple. Okay, g of x plus 2, so g of x was the square root of x minus 2, so this is the square root of x plus 2, we're replacing x with x plus 2, minus 2, so that's just, those brackets aren't needed, x plus 2 minus 2, so it's just the square root of x. H of y, now that just means taking all the x's and replacing them with y's, so it's just going to become 1 on y plus 2. 1 on y plus 1 is the function, isn't it? That seems really trivial, but that's a really important thing when you're working with your CAS. So if, for example, let's say you've defined a function over here in the calculator screen that's about h of t, okay? And h of t maybe is t squared plus or minus 5t, for example. I've just made it up. Let's say now we want to graph, and we're doing things over here, we're working out h of 0, we're solving h of t equal to 0 for t, whatever, we're working out h of 3, doesn't matter. Let's say then we want to graph it, and if we go over to the graphing screen, go to the graphing screen, press tab to open your entry line if it's not open. If you type h of t in here, your CAS won't sketch anything, and if you've got a newer operating system, it'll ask you, do you want to create a slider for t? I don't know what t is. Do you want me to substitute numbers in for t and you can play around and change the value of t and have a look at what happens to the graph? And no, we don't want to do that. I didn't mean to type h of t. It's important that you see that when you type in a graph, it is f of x, f1 of x. your graphing screen is always in terms of x. Now I don't need to redefine my function. I don't need to retype the rule for my function here. If I want to describe my function with x's in place of t's, I just type h of x in here. And now that is the graph of x squared minus 5x. So I'm looking at this graph. I just imagine that the x-axis is labelled as t instead. Okay, so that's a really important technique, just being able to, if your function is defined in terms of a variable other than x, simply typing f of x in the graphing screen will allow you to graph it. Okay, J, g of f of x. Okay, so this time we're going to put f of x into g of x. So that's f of x. We're going to make that the input to g of x. Okay, so it's going to be 3x minus x squared under that square root. So it's going to be the square root of, so essentially g of x is the square root of x minus 2. So g of f of x is the square root of f of x minus 2. And f of x is 3x minus x squared minus 2. Okay, there's no like terms under there, we can't collect that. You can reorder them if you want, but that's as simple as that's going to get. Okay, consider the functions f of x, where f of x is x squared plus 5x plus 6, so a quadratic function, and g of x, where g of x is 3x plus 14. Find f of 0, so that means replacing the x's with zeros. 0 squared plus 5 times 0 plus 6, so that's just 0 plus 0 plus 6, which is 6. If you're letting x equal 0, you're finding the y-intercept for f of x by working out f of 0. In B, we're finding the set of x values such that f of x equals 0. Okay, so f of x equals 0 means f of x is x squared plus 5x plus 6, and that has to equal 0. It's a quadratic that factorises x plus 6, x plus 1, and so x equals negative 6 or negative 1. It did ask us for a set, so if we're asked for a set, we should give our answer as a set, so therefore x is an element of the set of values that contain negative 6 and negative 1. Part C, the set of x values such that g of x is equal to 0. Okay, so g of x equals 0 means 3x plus 14 equals 0, or 3x is negative 14, so x is negative 14 on 3, which means, given we were asked for a set, x is an element of the set of values that include negative 14 on 3, so it's just one possible value. D, the set of x values such that g of x is bigger than 5. So g of x bigger than 5 means that 3x plus 14 is bigger than 5, which means that 3x is bigger than negative 9, which means that x is bigger than negative 3. Again, we want a set of x values, so x is an element of, an interval is a set, so I would use an interval here, negative infinity up to negative 3. Or you could say that x is an element of the set of x values such that x is less than negative 3. Okay, however you want to do it. E, the set of x values such that f of x is equal to g of x. Okay, so if f of x equals g of x, f of x is x squared, is it plus 5x plus 6? Yep. X squared plus 5x plus 6, and g of x is 3x plus 14. Alright, collecting like terms, subtracting 3x and subtracting 14. That factorises, it's x plus 4x minus 2. And so x plus 4 equals 0, which means x equals negative 4, or x minus 2 equals 0, which means x equals 2. And so therefore x is an element of the set of values that include negative 4 and 2. And finally, the set of x values where f of x is less than or equal to g of x. F of x less than or equal to g of x means x squared plus 5x plus 6 is less than or equal to 3x plus 14. which means that x squared plus 2x minus 8 is less than or equal to 0. Quadratic inequality. Over here we've already calculated where this graph equals 0. So it equals 0 at -4 and 2. So it is less than or equal to 0 between and including those values. Okay, when x is between -4 and 2 inclusive. So therefore x is an element of the interval from -4 to 2. Okay, then we get into our formal function notation that includes the domain, and we see this really frequently throughout the methods course. A function is only fully defined if both its domain and rule are given. The domain should only be omitted if it is R, but even in these cases it really should be included in this full formal, certainly if we're trying to be precise. When properly defining a function to include the domain and the rule, we use the following notation. Okay, so the bit at the start, f, that's just the name of the function. It doesn't have to be f, g, h, k, a, whatever. It's the name of the function. The semicolon, we've seen that a bit before, that means such that. So f, some function called f, is defined such that this bit here is the domain. Okay. So we have the name of a function called f. We're going to start with these input values, i.e. the domain, and we're going to turn them into output values. This is not the range. Okay, we're going to turn them into output values that fit somewhere in R. We call this the codomain, okay, and it's always going to be R in methods. It is just a set of values that would include the range. So in methods, it's always going to be R. The point is that we don't know what the range is until we know what the rule is, okay? So we're going to have a set of x values, we're going to turn them into a new set of values called the range, which will be some sort of subset of R, and we're going to do that using this particular rule. This is how we're going to convert the input values, the domain, into the output values, the range, which will be part of R. Okay, and then we've got the rule. So it's really only the yellow and green bits that are important in terms of knowing what's happening, domain and rule, but the notation is important to get right. Two functions that have the same rule, two functions might have the same rule, but if they have different domains, then they are different functions, because a function is defined by both rule and domain. Okay, so if the combination of those two things is different, then they are different functions. So for example, here we have g of x, it has the same rule, but because its domain is different, we can't call it f anymore, we call it something different, we'll call it g. Okay, let's consider the following relations, and if they are functions, then we rewrite them using formal function notation. Now, we can only use function notation if something's a function. So if it's not a function at all, we can't write it using this notation. We can't use f of x, g of x, whatever, if it's not a function. Okay, so here we've got a series of relations. So the first relation is a set of set of coordinates such that y is equal to 5x minus x cubed. So that's a cubic function. Okay, I'm going to call this, in fact, let's use the letters here. So I'm going to call this function a. Given that it's a cubic, the domain of all polynomial functions is R, the implied domain. If we're not given an explicit domain, we assume it's the implied domain. So the domain is R, the codomain will always be R, comma, and then we give the rule for a of x, which in this case is 5x minus x cubed. Okay, in part B, we're going to have function b. Now it's a linear function, but it's not written in a classic form, so actually we need to rearrange it because we need y to be the subject before we can replace y with b of x. So -5, let's make it 5y. I'm going to add that to the right and take away 20. 5y is 2x minus 20, and so y is 2/5 x minus 4. And so therefore, function b, it is a function, it's a linear function, so the domain of all linear functions is R, so domain is R, except that we've got a restricted domain here, so that gets included. So from 2 to 7, our codomain is still R, It's not the range, it's a set of values that includes the range, comma, and then we give our rule, b of x equals 2/5 x minus 4. Okay, part C. C is a circle, which is not a function. So we can't write it using this notation. X squared plus y squared equals 4 is a circle with a with centre at the origin and a radius of 2. D, that's a quadratic function. So it's a quadratic, and quadratics are all functions. And we've got the rule there, and we also know that it's only when x is bigger than 0, so that's the domain. So let's have function D. The domain is where x is bigger than 0. In this notation, we would generally use interval notation here. So domain is from 0 to infinity, or in this case, 0 to infinity is r plus. I would use r plus if I've got the choice. So r plus to codomain of r, d of x has rule x squared minus 2x plus 15. Okay, E, 1 on x plus 3, it's a rational function. The graph is a hyperbola, that's definitely a function. So the domain has an implied domain of r excluding negative 3. So we're going to have, I'm not going to use E here, I'm going to go to, let's just jump ahead to G because we haven't got part G here. E, just, E is approximately 2.718. It's a number, so I'm not going to use it as the name of a function. We need domain. Domain, as I said, is r excluding negative 3. Codomain is r. Rule for g of x is 1 on x plus 3. And f, it's a square root function. Okay, so we know that x minus 1 has to be bigger than or equal to 0, so x has to be bigger than or equal to 1, so that's going to give me my domain. So f, the domain is from 1 to infinity, codomain, and then the rule for f of x is square root of x minus 1. Your ability to understand and work with function notation, as I've said, is essential to being able to use your CAS well. Okay, so as I did over here, we did a quick example here. You might define the function in the calculator screen. Menu 1.1 is something you will do frequently in maths methods, which is define a function. It must be defined as a function, h of t, f of x, c of n, whatever. Okay, so it must be function notation so that you can use it. And then you can very easily make substitutions. You can very easily solve it equal to 0, as you can see in the calculator screen I did for that function I just defined. You can substitute other values into it. You might complete the square for it. Menu 3.5, complete the square for h of t, comma t. It'll complete the square, etc., etc. You can also graph it. Oh, sorry. Didn't mean to. You can also graph it as we did, but being careful that you must be in terms of x, so f of x. Just a word on using your CAS to graph. I would absolutely draw the graph and have a look at what it looks like, but I would not find any key points here in the graphing screen. Yes, you can use graph trace to find key points. Yes, you can use analyze graph to find turning points and points of axis intercepts, but I would simply draw the graph, have a look at it, see, okay, right, it's going to have x-intercepts that I need to find and a turning point that I need to find, and then jump straight back over to the calculator screen and do that algebraically here. So here's my x-intercepts at this line up here. They're t-intercepts, but they're at 0 and 5, and by completing the square, I can easily find the coordinates of the turning point. So think about what algebraic processes you can do. The flip side also works. So if I had, let me go back to my calculator, I'm going to hit delete, delete, delete to clear the graphing screen. If I draw the graph first, so let's have a different graph here. Maybe let's make it a cubic. Let's do it as x. I'll do it factorised just so I've got some idea of what it's going to look like. X minus 1 times x plus 1 times x minus 2. Okay, so it's a cubic, for example. If I then want to calculate things about this cubic, so for example the x-intercepts, now I know it's in a form that we can calculate those easily by hand, but just as an example, if I've drawn the graph first, right, I can see it, I'm going to need the x-intercepts, I'm going to need the y-intercept, I'm going to need the turning point. I go back over to my calculator screen and I'm going to solve f1 of x equals 0 for x to find the x-intercepts of that graph. I'm going to work out f1 of 0, substituting x equals 0 into the function to find the y-intercept of that graph. I'm going to solve, and this is a bit of a way off, we'll talk about this algebra later in the year, but I'm going to solve the derivative of f1 of x equal to 0 to find the location x values of the turning points. I'm going to substitute those values back in. So f of, for example, root 7 plus 2 over 3. I'm sorry, it wasn't f, was it? F1. See how it wasn't bold? So when I type f1, the text goes bold. That indicates that there's a function defined as f1. That's what I want. So that's the y value. Sorry, I didn't mean that. That's the y value of that turning point. And then we can do the same with the other one. It is negative root 7 plus 2 on 3. So that's the y value of that turning point. You can get them as decimals by pressing Control Enter. The other way you can find turning points without derivative would be to use menu 4 for calculus, but use function minimum. The problem with this one is if you did function minimum of f1 of x, you need comma x. It's going to tell you it's negative infinity. The minimum value of this function over the entire domain is indeed negative infinity, but maybe if I just restrict that to looking at when x is bigger than 0, that's going to give me the turning point. So function minimum, given that, so always restriction outside of the function itself, given that x is bigger than 0, then that gives me the x value where the function minimum occurs, and then I sub that back into my function. So a quick way to sub that back in, if you've just got the one solution there, f1 of x, given that, scroll back up, enter to copy that down, find f1 of x given that x is equal to this value, and that's a quick way to substitute it in using the previous line. We could find the function maximum, which is if we don't give it any restriction, so if I get rid of that restriction and instead make it function maximum, which is also available from the calculus menu, it'll tell me the function maximum is when x is infinity, and again because the graph gets bigger and bigger and bigger as x gets bigger and bigger and bigger. But if we find the function maximum when x is less than 0, we're going to isolate that turning point. So let me edit this one instead. So when x is less than 0, and make it function maximum, we'll find that the function maximum occurs there, and the y value then will be f1 of x, given that x is equal to that value, and that's the y value of that turning point. Okay, so playing around with, if you've got a question where you're going to be using that function to do lots of things, which happens frequently in this subject, you're going to define the function in your CAS right at the start so you can refer to it quickly and easily. That box just talks through some of the things we did then. You might also define the function by sketching the graph first, and then you'll use f1 of x in the calculator. Or you define the function in the calculator as I had h of t, there's d of t, an example here, and then have a look, and then you can sketch that graph by sketching d of x, and again you can use the function to calculate all the key points, the function definition to calculate all the key points. So there's two elements to what I'd like you to work on today, some questions from exercise 1b, reviewing function notation, and then a worksheet which is in Appendix B of your booklet, which is function notation using your CAS. So it's a series of problems that I want you to solve using your CAS, and try and play around with defining a function and effectively using that function definition to efficiently answer the questions using your CAS.